Hello. Today we're going to look at an example problem. Specifically, we're going to look at wave propagation. Wave propagation is an especially interesting example here in differential equations because it entails many of the things we've been working on. So it entails, for example, it entails a boundary value problems. It entails eigenvalues and their corresponding eigenvectors, right? It also is going to entail Fourier transforms. And all, in the end, is to try to solve second order differential equations. So let's see if we can go ahead and look at a specific example of a wave equation and actually get to the point in this lecture where we can actually solve it and see a wave moving. So what we're actually going to attempt to get to by the end of this lecture is, let's say I have something like a guitar string which is held tight at both ends, and let's say I put my finger on it and pluck it. Let's say it looks like this, and it's fixed at both ends, and then I let this go. What do I expect to happen? What does the mathematics tell us will happen? Well, we can guess, for example, that this wave is going to propagate right down this wire and hit the edge and bounce back, and something like that is going to happen. How exactly is this going to happen? How can we determine it mathematically? That's what we'll look at today. So, starting off with the wave equation. The wave equation is often written or looks something like this. So this is the one-dimensional wave equation, and so this is a 1D wave equation, where u is going to be a function of both x and t. And in this case, u is just the deflection of the wire, the string, or the rope we're talking about. So let's assume that this wire, string, or rope can only move in the y, let's say up and down, right? But of course, the up and down motion depends both on the horizontal position, which is x, and the time we're looking at, which is t. All right? As this is a differential equations class and not a physics class, we're not going to go too deeply into how this equation is derived, but you can derive this equation simply from the properties of the string. And something that's interesting that we will need to know is that, notice we have v here. V is actually the velocity of, well, in this case it's the speed, but this is the velocity of a wave in the rope. So if this was air, this would be the speed of sound. If this was light, this would be the speed of light. This is the velocity a wave will travel, and we'll see how that's important as we move forward. Typically, when you see this kind of equation, we're going to make the assumption that let's say we can write u of x and t as some function, and I'll just call this big X of x times t of t. All right? This is often called, well, we've done this before in differential equations, this is a separation of variables. I can write the combination function as a product of two functions. So let's go ahead and see what happens when we plug that in to this equation. When we plug that into this equation, right, the partial derivative with respect to t doesn't care about x, it just treats it like a constant. So therefore we're going to get the second derivative of t times x for this side. And then we're going to get v squared times this side, doesn't care about t, only cares about x, is going to be the second derivative of x times t. This is an interesting equation. And we need a little bit more information. And in this case, that little bit more information we're going to need comes from the boundaries, right? This is often called a boundary value problem, right? So let's just write that, a boundary value problem. And this means exactly what it says. It's a problem where we know the boundaries. In differential equations, we often look at problems where we have some differential equation, x double prime equals dot dot dot, fine. And then we have x of 0 equals something, and x prime of 0 equals something. This is what's called an initial value problem, right? Sometimes you're given this kind of information. But in this case, we don't necessarily know the conditions at a certain point in time. Here we know the conditions at the boundary, right? Namely the ends of our rope, all right? And different kinds of systems have different boundary values, all right? And we've seen some of these. For example, if you have a rope that's tied between 2 points, the boundary value is that y of 0 equals 0 and y of L equals 0. This is because at these points, the rope can't move. And so the boundary has to obey those conditions. So we know that any function has to obey those conditions. So we can have something that looks like this, but we can't have anything that doesn't obey these boundary values. This is also what you have when you have vibrations in a tube, for example. You can also have boundary value problems where, for example, well, an open musical tube often has boundary value problems that look like, or waves that look like this, where sometimes this would look like a closed end and an open end. So for example, here we'd say something like y of 0 equals 0 and y prime of L equals 0. Or in other words, the derivative has to be 0 at the other end. This is a different kind of boundary value problem, right? But it's still a boundary value problem. Namely, we're given a conditional statement on the function at the boundaries. And it's not necessarily on the function, it can be on the derivative of the function as well, right? We have these also in many situations. You'll see these in acoustics, you'll see those in electrodynamics, you see these in quantum mechanics all the time as boundary value problems. And boundary value problems often lead, or in this, especially in this case for differential equations, lead to eigenvalue eigenvector equations. So the ones we've typically been dealing with were something where we have, for example, x double prime is proportional to x, or minus x, as it were. If x double prime is proportional to minus x, right, this means the solutions are going to be, and well, let's just write it as a normally kind of equation, would be x double prime, well, how's it? Well, let's just say plus lambda x equals 0. This would be the normal eigenvalue eigenvector equation. The solutions to this, for example, are the sine of, let's make this lambda squared to make our life easier, right? So the solutions to this equation are the sines of lambda times t or the cosine of lambda times t. And of course, we can have any kind of constant out in front we want. So this equation tells you, so just given the equation, just given this part, we know what the solutions are. But eigenvalue, eigenvector, boundary value problems actually give you more information. That is to say, if we also know that this and this has to be true, that puts limitations on the acceptable lambda values we can have. So if that's the case, and that is the boundary value problem we're most interested in that case, I can only have lambda values which allow me to have values where it's 0 at the edges. So in this case, my boundary values, I can only have x in this case, my x of x function, my capital X of little x function, can only be functions that look like the sine, in this case, of lambda x, right? And lambda has to be in pi over L. Okay, so this is the standard boundary value problem, and it can only be these values because, and it can't be cosines because cosine of 0 is not 0. So it can be any sine functions because sines always start at 0, but if this is L, it has to be 0 at L. So this, of course, works, right? And that works because this is pi, and the sine of pi is 0. But it can't be pi over 2, because then we'd get this, right? And if this was our guess, this doesn't fulfill that boundary value condition. All right? So, for our given case, for our string, and now let's get back to our actually thing that we wanted to solve. Remember, we have a string of length L. We already worked out the boundary value problem. So we know the spatial part. The spatial part, namely x of x, is going to equal the sine of n pi x over L. All right? These are the only possible functions I can have that fulfill that condition, where of course n equals an integer. Now let's go ahead and put that back and see what happens when we put that back into, well, our wave equation here, which we decided looks like this. If we put that back into our wave equation, then we also know that x double prime, or let's be a little bit careful here. Let's say dx squared of x is going to equal minus n squared pi squared over L squared times the sine of n pi x over L. All I'm doing is taking the second derivative of this, the second partial derivative with respect to space. And of course, each derivative is going to bring out this argument, so it's going to be that argument squared times the number of itself. And notice that this just equals minus n squared pi squared over L squared, this is pi squared, L squared times x itself, right? So now we're back to this interesting situation that we expected to happen, this eigenvalue, eigenvector situation, where the second derivative of a function equals a number times the function. This is a typical thing we'll see for an eigenvalue, eigenvector equations. And we know the spatial part. So let's go ahead and plug that back in. And if we plug that back into our wave equation, we're going to get the partial derivative. So t double prime, the second partial derivative of t, times x is going to equal v squared times n squared pi squared over L squared times x. All right? All I'm doing is putting everything back into this equation. All right? So x is just x, and the second partial derivative of x with respect to is what we did here. So I just plugged this in for what we did. Okay? And of course, I can't forget the t, right? That's this t here. All right. This is interesting because now the x part goes away, and I just get the second partial derivative with respect to time is just going to equal v squared n squared pi squared over L squared times t. Well, that's nice because now I have a very symmetric kind of problem, right? We see that the spatial part of the problem influences the temporal part of the solution, and we get a temporal eigenvector problem back out, where the second derivative of a function equals a number times a function. And this means, in this case, oh, I forgot the minus sign here. Sorry about that, right? This minus sign, right, has to come through here. So given that that's the minus sign, then my only possible solutions are that t can be equal to the sine of something, but that something, when I take the second derivative of it, has to give me this number back out. So it's going to be the sine of v n pi t over L, or the cosine of v n pi t over L. And we can write, let's say this is a and b, right? Okay. So hopefully this is clear that these can be the only solutions, because if I plug t back into here, what's the second derivative going to be? Well, the derivative is just going to output this part, right? So the first derivative would be a times v in pi over L cosine of this stuff, and we go sine to cosine, and then the next derivative would be a v squared n squared pi squared over L squared times a sine with a minus sign, and this gives back this, so that means this equation is true. All right, so now we've solved for the spatial part and we've solved for the temporal part in the eigenvalue eigenvector equation. We can put them both together now to look at the full wave equation. So remember our full wave equation, u of x and t just equals x of x and t of t. And we already figured out what those are going to be. That's going to be the sine of, let's see, so that's going to be the sine of n pi x over L times, and I'll write it like this, a times the sine of v in pi x over L plus b cosine of the same thing. All right. So this is our generalized solution, and these are the eigenvalues, eigenvectors. These are also what are known as the standing waves. So let's look at what one of these might look like. So if n equals 1, this is just going to be the sine of n pi x over L. So this is just going to be this. And this tells us how this thing is going to vibrate. Namely, this thing is going to vibrate, right? This is a t. So this thing is going to vibrate with an angular frequency of v times pi over L. So omega 1 just equals v pi over L. And that tells me how fast this is going to vibrate up and down and up and down. That would be the n equals 1 mode, right? So the nth eigenvector is this function, the nth eigenvalue. What about if n equals 2? Then it's going to be the sine of 2 pi x over L, which is just this sine function, and it's going to vibrate with 2v pi over L, all right? This tells us how fast it's going to vibrate up and down. And in this case, notice this vibration. So it's going to start up, and then it's going to move to something like this. Then it's going to be flat. Then it's going to move to something like this. And then it's going to move to something like this, right? So the more nodes, the higher the frequency of oscillation. And hopefully you've seen a demonstration like this with a vibrating string, and you can make these nodes. Okay, so now we know, and these are what are called the standing waves. All right, so these are the standing waves. Great. These are the eigenvalues and eigenvectors, and we know some solutions, right? These are all possible solutions to this equation. But if you recall, way back here, we didn't want to look at the standing waves. We wanted to look at a particular example. So how are we actually going to get this wave to propagate out, right? Well, we're going to project onto these waves that we know what the solutions are, all right? And you'll notice that these waves are just the Fourier series, right? So this is just the discrete Fourier series we got back out. So we need to project onto these waves and see how they act. Because when you have an equation like this, not only is each one of these an answer, this is a superposition principle, so any combination of the sum of these is also an answer, right? So I'm going to break it down into how much looks like this, how much looks like this, how much looks like the next thing. I know how each component vibrates, and then I'm going to add them up as time propagates to get the answer. All right, so let's say we know, for example, f of x and 0. So this is my initial function, or I'll call it the initial shape. Remember, this is our something that looks like this. And what I really want of f of x and t. So how am I going to get this? This is where we need to start to do this projection. So I can write, for example, that, so f of x and t can be written as the sum of the standing waves, right? So I'm going to call these amplitudes, I'll just call them A. So A sub n times the sine of n pi x over L. This will give me the spatial part, right? And once I have the spatial part, then I need it to vibrate. In general, you need to keep both these A and the B's, but for us, I'm just going to keep the second component just because the sine of 0 is 0, right? So I'll assume that I just have this steady state wave and I don't need this. In general, you should keep track of both A and B, but just for this example, I'm gonna get rid of this A and just keep this part. So we'll have also the cosine then of v in pi t over L, right? So this is basically the spatial part. This is the temporal part, right? And this is how much, right? So it's how much it looks like this, and it vibrating up and down in time, and how much it looks like this, vibrating up and down in time. And remember, typically I need both of these to keep track of this. Here I'm just gonna make my life a little bit simpler by doing this, right? So yeah, again, warning, I'm making a move here that you shouldn't assume is true. Typically you need the A and the B to keep the phase. Here I'm just going to keep the B just to make our life a little bit simpler. All right, so proceeding on then, this is all good, but I need to know how to deal with what A is. All right, A is how much it looks like each of these modes, and this is again going to look a lot like our Fourier transform. So A of n is just how much our function looks like each of these, and we should know by now that asking them a question, how much does one function look like another, just means taking the integral of one function, namely f of x and 0, multiplying it by the sine of n pi x over L times dx, and of course we need this 2 over L normalization factor. So in this case, this should be the entirety of the solution. This allows it to vibrate up and down and travel in time. Okay, so just to recap before we actually look at this example, moving in time, realize that all we did was basically an eigenvalue eigenvector equation in X. We use a solution, right, in X to realize that we actually have another eigenvalue eigenvector kind of equation, a second order differential equation in T. We solve that time in T to get the full equation. Once we had the full equation, then we were able to use our initial, so these were boundary value problems. Then we used the initial shape and projected on this basis set to see how the whole thing is going to act. Now let's go ahead and take a look and see if this works out in practical example. So let's switch over here. So I'll do this in started. Let's see here. appeared that there was some audio problem there for a second. I hope I've got that fixed, so now I think you can hear me again. All I've done here, just to recap, was I just set a few values. So I said L equals 1, that's our length. I said the velocity equals 1. This velocity is determined by the tension in the rope, for example, and how heavy the rope is. And then I just looked at, this is what the first standing wave looks like, and this is what the second standing wave looks like. We see that each of the standing waves basically vibrates at a different frequency. All right? So that's interesting. So now we can start to build what the actual function is. So let's say, I'll just call it f of x. Let's just say it's this x minus 5 squared. Okay, so I'll just make it a Gaussian function here. So this is a very simple function that looks like a function that is going to happen when I pluck the string. All right, so it's also nice to think about what we think is going to happen. So if I pluck the string like this in the middle, what do I think is going to happen? Well, I think it's going to propagate to the right, and I think it's going to propagate to the left in this picture and bounce off the edges and come back. And if we do things right, we might even get that it does this with a speed of 1. All right, so let's go ahead and do that. So what do we need to do to actually see that this is working? Well, we need to find our coefficients. So A1 is just going to equal 2 divided by L, and then the integral from 0 to L of f of x, times the sine of pi x divided by L dx, and hopefully I get a number there. Good. So this is going to be our first order approximation. Let's see how well we did. Let's stop our time here real quick and put the time back to 0. So let's see how well we did. So we'll just call this, I guess we called this u of x. So u of x in this case just equals a1 times this All right, so this is our first guess, and if I let the time run, let's move this up here. We don't really need these functions anymore. All right, so if we let our time run, we can see that it just looks like this initial wave moving back and forth. But that's just the approximation of the first component. So A1 is how much our initial wave looked like that component, and we can see it's just bouncing back and forth. But as we add more waves, this should get better and better each time. So let's go ahead and we'll move this back to 0. Let's add the next component. So the next component is just going to look like this component. So we'll call this A2, and this will be a 2 here. And we can see A2 looks like 0. That's fine. We can put that in. Let's not forget our 2's here. So we have A2, and we can just keep going. Let's add one more. A3. It's going to be the same thing with a 3 here. And A3. And you can see now our wave function is actually starting to look a little bit like the initial wave function, right? The more components I add, the more it's going to look like the initial wave function. And if I say play, well, it might actually look like something realistic, right? So it's starting to look more and more realistic as I add more and more terms to this thing moving up and down, all right? And notice that this is formulaic, so I can add anything I want. So I could actually move this over to a different position. So let's say I start the wave to the left. I can also play that, and I can see the wave basically move back and forth from the left side to the right side, back and forth. I can make it narrower as a starting position, right, or wider, or move it left and right, and see the wave function move back and forth. And the more components of these standing waves that I add, then more and more that it's going to look correct. So let's go ahead and we'll finish this video up by seeing how you can do this, right? You can just keep adding this in Desmos, for example. Of course, you can write this as a sum, right, from 1 to 4, let's just say. And I can do it like this as well and plug these components in, right? So this is going to be the sum of the integral, then times each of these components times the time part. You can also do it that way, and that works fine. Just notice that Desmos starts to move pretty slow once you get past 4 or 5 time iterations. But it's a good exercise to play with that a little bit. But to actually do this a little bit quicker for you, I'll show you some simple code that does the same kind of thing. It's not that important that you understand what's going on in the details of this code, but to recognize that it has nothing different than the parts we've already discussed. So all I'm doing in this code is, this is our initial, this is just defining some parameters, it doesn't really matter. This is our initial function, so I need an initial function, and we'll play with this initial function a little bit. So this is our initial function. Then I need to project onto this basis set, right? Projecting on the basis set again is asking how much this function looks like in each of the eigenvectors. And that's just an integral. In numerical, this just means the integral. The integral is the sum. So it's the integral of the original function times the sine of n pi x over L dx. So this is just the integral, and of course we need 2 over the L. So these a's are just the a components. That's fine. How do we propagate in time? Well, to propagate in time, then what we do is we basically just evolve it in time. So where this is just evolving in time, and this is just plotting. So you notice this program is actually incredibly simple. Define the initial function, project on the eigenvalues and eigenvectors, and then the time-dependent function is just each one of those coefficients times the sine of n pi x over L times the cosine of v times n pi t over L. So that's all it's doing, and then we can just plot this. So let's go ahead and quickly bring that up. Hopefully I can do both of these on top of one another. So here's now the graph of this when I run this code really quickly. Yeah, so you can see what happens. The time is on the top, so you can see at the very top. Let me move this down ever so slightly so you can see it and move it this way a little bit. There we go. So the time is on the top. And you can see how this wave propagates back and forth. Okay, so let me just speed this up a little bit for you. And run it again. So that's a little bit faster. So you can see I started with the initial wave. The wave then propagates and moves from the left-hand side to the right-hand side. Okay. So let's go ahead and look at that one more time. So we can go ahead and propagate it again. So again, we're plucking it on the left-hand side. We have the wave function moving both to the right and the left, and then it hits the side, basically the end of the string, and bounces off, and then bounces around. So this is a much more realistic representation of what's going to happen in the wave, and this is with only 20 components. So you can see it's happening very fast. It's doing the calculation in real time. As you watch this movie, you'll also notice something else that's interesting, and that is that the wave itself is propagating across the string. Remember, the string had a length of 1, and we plugged in a velocity of 1, and so the time it takes the wave to move should be about 1, in this case, let's say meters per second. So even though the velocity is only incorporated in this very strange way in the differential equation, it comes back out in exactly the wave propagation speed, right? So even though the velocity just affects how fast each of the standing waves vibrates up and down, it actually turns out that that is going to be the velocity of the wave. And of course, we can make smaller and smaller waves, narrower and narrower if we wanted to. So, well, if I wanted let's say a narrower wave, I could do that as well. So you can see, right, I plucked the string, I dropped it, the wave is now propagating to the right. You notice there's also this wave chasing it. That's the part of the wave that propagated to the left, hit the edge, and now is bouncing back. And you can see that they take about 1 unit's time, right? It didn't start exactly at 0. That's why it's not exactly 1 when it reaches the other edge of the string to move all the way across, right? And I can have any kind of wave I want, and I can start, let's say I start in the middle, all right? So what if I started a wave in the middle? I'd expect it to propagate both to the left and the right, hit the edges, and bounce back. Well, is that what I get? Lo and behold, that's exactly what I get. So indeed, this method gives us the real propagation of how a wave acts physically, and it comes from this simple technique. So that will be it for now. Just to give a very quick recap, remember how we solved this problem. So let's switch back really quickly to the paper. If you lasted this long, just remember what we did. All we did was use the wave equation. From the wave equation, we found the x part, the spatial part from the boundary value problem. We then used the x part to find the temporal part, and this is how we know this vibration of the temporal part is actually related to the vibration of the spatial part. We then plugged these back together. We projected our initial wave function onto this basis set because we know how each of the components of this basis set act in time, and then we sum them up and then through superposition see how they all act in time. All right, so we'll go for more examples on this later, but I hope this is a good introduction to solving this kind of problem. Thank you.